Back in algebra, you learned about inverse functions. And an inverse of a function is one in which the x values and the y values have been reversed from the original function. So for example, if your original function is the points 3, 2, 5, 1, and 4, 7, your inverse function would be 2, 3, 1, 5, and 7, 4. In trig, if y equals sine of x is the original function, then its inverse is represented by y equals arcsine of x, or y equals sine with the -1 exponent of x. These mean the same things. We actually say the sine with the -1 exponent as inverse sine. These inverse relations are the angles' arc lengths. That's why we get the name arcsine, whose sine equals x. If we wanted to take the expression sine of x equals square root of 3 over 2 and rewrite it using an inverse trig relation, we would write either sine inverse with the -1 exponent, radical 3 over 2 equals x, or we could also write the word arcsine, radical 3 over 2 equals x. Those both are asking the same thing. When we see this notation of inverse sine of radical 3 over 2 equals x, or arcsine of radical 3 over 2 equals x, what this means is that we are looking for the arc length, or the angle, for which the value of the sine, the y value, is the square root of 3 over 2. The problem is that there are two angles for which the sine is radical 3 over 2, and we only want one answer. In order to accomplish this, we limit which quadrants we use. We want one quadrant for positive answers and one quadrant for negative answers. And we want these quadrants to be adjacent, which means side by side. This figure that I have put into place here now shows which quadrants we use. If we have an inverse sine function, we use the first and the fourth quadrants. The first quadrant gives us our positive values of sine, and the fourth quadrant gives us our negative values of sine. For an inverse cosine function, we use the first and the second quadrants. The first gives us positive values for cosine, and the second quadrant gives us negative values for cosine. For tangent, we go back to the first quadrant and the fourth quadrant, the first for positives and the fourth for negatives. So because of these limitations on quadrants, if we want to go back to our original problem, which is to find where the sine inverse of square root of 3 over 2 equals x, we must use only the first quadrant. So now to answer our question, we are looking for which angle in the first quadrant, because it's positive, has a sine of radical 3 over 2, and that angle is pi over 3. So our x is pi over 3. On example 1, we are going to find the exact value of y in radians. On A, our problem is y equals the inverse cosine of -1. You are asking yourself what angle in radians in quadrant 1 or quadrant 2, because this is cosine, has a cosine of -1. Well, that happens at pi. So your answer here would be y equals pi. On B, we have y equals the inverse sine of 0. So you are asking yourself, in quadrant 1 or in quadrant 4, because this is sine, where is the sine value equal to 0? What angle has a sine value or a y value of 0? That happens at 0 radians. On C, you are asking yourself, what angle has a cosine of 1/2? It's positive, and so it must be in quadrant 1. Since it's cosine, we want the x value. What angle in the first quadrant has an x value of 1/2? That angle is pi over 3. On example 2, your directions will say find the exact value of the expression, and this is problem type 1. The first problem that we're going to do is the cosine of the sine inverse of 2/3. Just like any kind of problem, when you have grouping symbols, you want to work from the inside out. So the first thing we're going to look at is this sine inverse of 2/3. Check the sign of the number. Is it positive or is it negative? It's positive. So what that means is that we are going to use quadrant 1. So what we are going to do is set up an angle in quadrant 1 where the sine relationship of y over r is 2/3. Now we have to use the Pythagorean theorem to find the x value. So x squared plus 2 squared equals 3 squared. X squared plus 4 equals 9. X squared equals 5. So x has to be either positive or negative square root of 5. Since we are in the first quadrant, it has to be positive square root of 5. So what we have done by setting up this picture is we have created an angle whose sine is 2/3. We now want to do the cosine of that angle. So the cosine of that angle theta is the x value, square root of 5, over the r3, and that's your answer. On B, we want to do the sine of the arctangent of 3/2. This is no different than the first in the way we're going to approach this. We're going to work on the inside first. We want an angle whose tangent is positive 3/2. If we're doing positive for any of these angles, it's going to be in quadrant 1. So we are going to set up an angle theta where the tangent relationship of y over x is 3/2. Now we need to do the Pythagorean theorem to find the r value. So 2 squared plus 3 squared has to equal r squared. 4 plus 9 equals r squared, so 13 equals r squared. Technically, r is plus or minus the square root of 13, but remember, r is always positive. So r is the square root of 13. Now we want to go and do the outside part. We want to do the sine of that angle theta. Well, the sine is y3 over r square root of 13. You do not need to rationalize it. You can leave your answer like that. On example C, we want to find the tangent of the arc cosine of -5/13. The inside set of parentheses is just for readability so that you can see that it's -5/13. So we have to think about, this is a cosine function and it's negative. Where is cosine negative? We are using second quadrant for cosine. Tangent and sine are fourth quadrant for negative, but cosine is second quadrant. Set up a relationship where the cosine x is 5, r is 13, the x gets the negative. Do your Pythagorean theorem to find the y value. Negative 5 squared plus y squared equals 13 squared. So we have 25 plus y squared equals 169. Y squared equals 144. So y has to be plus or minus 12. In the second quadrant, y is positive. So y is positive 12. Now we want to do the tangent for that angle theta. The tangent is going to be the y over the x, so we're going to have 12 over negative 5. Done. On example 3, we are going to be doing the same thing. We're still finding exact values for the expressions. What's going to be different is they're going to give you different kinds of functions here. They're going to go to cotangent, cosecant, secant. So work the inside just like we were doing before. Tangent has to be negative 9. Well, tangent's negative in quadrant 4. So we're going to set up an angle that's in quadrant 4, and the tangent relationship has to be negative 9. Well, if it's just negative 9, remember that that's negative 9 over 1. So y is 9, x is 1. What gets the negative? In fourth quadrant, it's the y. Now do Pythagorean theorem to find the r value. So you will have 1 squared plus negative 9 squared equals r squared. 1 plus 81 equals r squared. 82 is r squared, so r is the square root of 82. I didn't write down the plus or minus because r must be positive. So r is the square root of 82. So this picture now illustrates everything about the inside. We now want to do the cosecant of that theta. Cosecant is r over y. Our r is the square root of 82. Our y is negative 9. There's your answer. On B, we want to find the cotangent of the inverse sine of negative 7/8. If we have a sine and it has to be negative, then we need to be in quadrant 4 again. So we're going to set up an angle in quadrant 4 where the sine relationship y over r will be negative 7/8. Do Pythagorean theorem, you're going to have x squared plus negative 7 squared equals 8 squared. X squared plus 49 equals 64. So x squared has to be 15. So x has to either be plus or minus the square root of 15. Quadrant 4, x is positive. So it's going to be positive square root of 15. Now that we have set up a sine relationship of negative 7/8, we want to do the outside part of this and do the cotangent of that theta. Cotangent is x over y. So we're going to have the square root of 15 over negative 7. And that's our answer. On example 4, we are still finding the exact value of the expression, but this is a third type of problem. What's going to be a little bit different on these is that the arc sign might be on the outside instead of the inside. The inverse function might be outside instead of inside. They're going to kind of mix them up on you. So you are still going to work from the inside out. On this one, the inside part is tangent of 7 pi over 4. So use your unit circle, find the tangent of 7 pi over 4. Well, tangent of 7 pi over 4 equals -1. So now what our problem becomes is arc sine of -1. We replaced tangent of 7 pi over 4 with what we know it equals. Now we're doing a simple inverse function. Ask yourself where in first quadrant or in fourth quadrant does the sine value equal -1? When we use the fourth quadrant, we are going down from 0, and so that happens at -pi over 2. On B, we want to do the arc sine of the cosine of 4 pi over 3. So the first thing we're going to do is think about the cosine of 4 pi over 3. What does that equal? That equals -1/2. So we are going to replace cosine of 4 pi over 3 with what we know it's equal to. And that means our problem becomes the arc sine of -1/2. Now we are going to ask ourselves, in fourth quadrant, because it's negative, what angle has a sine or a y value of -1/2? That happens at -pi over 3. On the last example for these problems, we have to do the cosine of the inverse tangent of the square root of 3. So again, working the inside first. The inverse tangent square root of 3. What angle has a tangent, and this must be in quadrant 1 because it's positive. If you put the y over the x, where do you get square root of 3? That happens at pi over 3. So now our problem becomes the cosine of pi over 3. Well, we know that the cosine of pi over 3 equals 1/2.